All right, welcome. So my name is Filip, and this is a session about the upcoming Doomsday, or as we like to call it, the Q-Day, which is the day on which quantum computers will be able to break some of our existing cryptography. So first of all, thank you for coming. I really appreciate you coming. I really do, especially as, you know, I had a look at the agenda, and I can safely tell you that every single session that is happening in parallel to this one is actually better than this one. So from that perspective, you may have not chosen wisely, but I'll do my best to make it as useful and as interesting as possible. Now, as I mentioned, my name is Filip. I do have a last name, but nobody can pronounce it, including me, so I typically just say Filip W. Now, there's a legend that somebody pronounced my name correctly once and then immediately died. So, so there you go. So I'm a Microsoft MVP in the category called Azure High Performance Computing. Now, this is a bit cryptic, but what is buried in there is actually the field of quantum computing. And so if you'd like to learn more about quantum computers, then I have this book recommendation for you. So this is a book that I wrote a while ago. Now, I always recommend this book to people because I really like the author. But, the point is that today we are going to look at quantum computing from a different angle. Namely, we are going to sort of consider quantum computers to be the threat actor and see how we can protect ourselves from that. And so this is the rough agenda for today. We'll start with a little bit of a warm-up, just to make sure that everybody's on the same page. So this will be some super basic stuff, just to align everybody. Then we will talk about quantum threats. We will talk about quantum computers and sort of what they do, that they are actually efficient at solving certain types of problems. And then we'll talk about post-quantum cryptography and sort of how we can protect ourselves from that. And at the end, we'll have a look at some code. It'll be .NET code because that is in the subtitle for this session. So there we go. So here's the warm-up. So the warm-up question is as follows. Is it possible to have unbreakable encryption? Right? I promise you that this is not a tricky question. We will not have to invoke any quantum concepts to actually be able to answer it. Now, I would like you to think in your head for about two seconds about this and come up with the answer. And the answer to this question is actually, and this is surprising to some people, at least to the people that answer wrongly, the answer is yes. Now, what is even more surprising is that the scheme that guarantees this is unbelievably simple. In fact, it's so simple, you can go home and teach your child how to do unbreakable encryption, because that is the technique that we call one-time pad. Okay? Really, the only skill that you have to have here is to be able to convert a payload to binary, right? So you start with a message, you convert it into a binary format, then you generate a random key that has at least the same amount of bits, so it has to have the same length, or might be longer as well. And then you just go through the individual bits of the message and the key, and you apply XOR logic between them. And XOR, exclusive OR, means that a 0 and a 0 would give you a 0, a 1 and a 1 would also give you a 0, but a 0 and a 1 would give you a 1. That is it, right? That is your ciphertext. And you can always recover the original message from the ciphertext by repeating the same procedure, but now between the ciphertext and the key. Now, this is not unconditional. You have to meet certain prerequisites. So first of all, the key must be at least the length of the message, because otherwise you run out of bits. The second thing is the key must be completely random, so you need a really good source of entropy. And finally, the key must never be reused, right? So this is why it's called a one-time pad. Now, if you consider all of this, it's just not very practical, this technique, right? Because you have super long keys, you have to change them all the time. Now, an interesting aspect of this is that this can be combined very nicely with the emerging quantum communication technologies, but this is something that is really not relevant for us today, so we'll not dive into that. But this is something that is used in some places. It was used quite a lot in the past as well, like, for example, in the communication between the Soviet Union and the United States during the Cold War. Like, they literally had like long sheets of pre-shared one-time pad keys, and they would just use that to encrypt messages. We can actually prove that if you fulfill all these criteria, that this scheme is actually mathematically theoretically secure. Like, you gain zero information by intercepting the messages, and there's like no pattern that you can use to attack this, other than just guessing. But because it's just because it is not really practical, we have other schemes that we use. But overall, one-time path falls into the category of symmetric encryption, right? And the symmetric encryption basically relies on the fact in communication scenarios that two parties share the same key. You can see that there's a yellow key here, and I mean, the fact that it's yellow on both sides proves that this is really the same key. Now, in this case, a key and the message produces a ciphertext, and the ciphertext and the key produces the message back. And out of this class of symmetric algorithms, AES is by far the most widely used. And in fact, we have so much trust in AES that we think that it will not be vulnerable to quantum computing attacks, but we are going to come back to this later. And even like the national security agencies across the world, they use AES for encryption. Now, symmetric encryption is great. It's fast, it's relatively simple, it's reliable, but of course, it has the chicken and egg problem if you use it for communication, right? If you'd like to use symmetric encryption to create a secure communication channel, then you need a secure communication channel in the first place to be able to agree on the key that you are going to use with your counterpart. And this is, of course, why we have asymmetric encryption. And now, in this case, we have two keys that are different from each other, and these are private and public keys. And the gist of asymmetric encryption is that the public key is derived from the private key. There is a mathematical relationship between them, right? And the way this works generally is that it is easy to go from private key to public key, but it's almost impossible to go the opposite way, right? Theoretically, it is possible, but it's just super difficult. So to recover the private key out of the public key. And within this scheme now, anybody can encrypt something with the public key, but only the person with the private key can decrypt it. And the same scheme can also be used for signatures, where data can be signed with a private key, and then the public key can be used to verify the integrity of that. And these are basically the two common scenarios for asymmetric encryption. The key exchange establishment, so for example, in TLS, we would run the initial handshake using asymmetric encryption and switch to AES because it's better, right? And then digital signatures, of course, something that is widely used as well in places like authentication tokens. Like this is a JOT token here, and the blue part here, this is the signature, right? And this way, anybody who's consuming the token can then verify the authenticity and integrity of this token. And so just to summarize this, I mean, asymmetric crypto is based on difficult mathematical problems, right? So this key derivation going from private to public, that depends on these two problems here. So these are the two major branches of asymmetric cryptography, if you will, RSA and elliptic curve cryptography. And then the problems at their heart are different mathematically, but if you reduce them down to like the bare minimum, you will actually see that these are the same, but we are going to come back to this later on. So this was just a warm-up, and let's now talk about some quantum stuff. So before we get to anything useful, I wanted to spend maybe 5 minutes talking about how quantum computers work. And the basic unit of information in quantum information science is a qubit, a quantum bit. Now, a qubit can be observed to be in one of two possible states. And in that sense, it is like a regular bit. Now, from the quantum computing community, we call bits, regular bits, we call them classical bits. In fact, we call the entire binary computation classical computation, right? I mean, we do it because we don't want to call it legacy, right? So we're being nice, we're calling it classical. So when you hear me refer to classical stuff, I don't mean like ancient Greece, I really mean the computation that we use today and the current information theory that we use. And so a bit can only be a 0 or a 1. Now a qubit can only be observed to be in one of two possible states. Now these states are shown here. This symbol is called a cat 0 and cat 1. This is notation from quantum mechanics. It's called the bracket notation, or even better, Dirac notation, after Paul Dirac, who, I think, the third greatest scientist that this country has ever produced, right? After Newton and Maxwell. So this is cat 0, this is cat 1, and a state of a qubit is actually a vector. And so basically Dirac notation allows us to write vectors in a shorthand fashion. And so these are really just vectors. But fundamentally, if we stop here, basically what we've done is we've reconstructed classical computing on a quantum computer, right? Because, I mean, there's this one-to-one correspondence between the observable states and the bit value 0 and bit value 1. So you can think of quantum computation as being a superset, conceptually, of classical computation. But of course, we will not stop here, right? Because a qubit can also be in a superposition state. And the superposition state is something that can be visualized for a single qubit on a Bloch sphere. So this thing is called the Bloch sphere. It's called Bloch sphere because Felix Bloch used it for the first time, but it's just a sphere. There's nothing special about it. And so we start here at the center. And if I draw a vector that points to the North Pole and another vector that points to the South Pole, those would be my states ket0 and ket1. But I can actually draw from the center towards any other point on the surface of the sphere. In fact, I can come up with infinitely many of such vectors. And actually, all those other vectors are also valid states of a qubit. They are simply different ways of mixing the states ket0 and ket1 together. So mathematically speaking, this is a linear combination of both ket0 and ket1. Right? Now, the thing with superposition is that we can never see a superposition, right? So we can only observe the observable states. That's why they are called observable states. So we cannot ever walk up to a qubit and say, hey, qubit, which state you are in? And then it will say, oh, thanks for asking, I'm in a superposition. It will always say, I'm in a state ket0 and ket1, these observable states, right? I mean, there can be other pairs of observable states, but this is not relevant for us. So now this has a lot of really strange philosophical consequences, because if the qubit is in a superposition state, then it is effectively in this sort of mixed state of both of its possible outcomes, of both of its possible values, right? And this then leads to many philosophical paradoxes, of course, the most famous being the case of the cat of Erwin Schrödinger that was both dead and alive at the same time, right? If you consider being dead and being alive to be the two observable states, then when the cat is in a superposition of both, then it is really both dead and alive at the same time. It's not that we don't know whether it's living or not, but it's really in this mixed state, right? So we will not resolve this paradox here today, but I just wanted to highlight it because quantum mechanics is weird. Now, when the program evolves, like what happens in a computer program? Like at the highest possible level, in a classical program, everything can be reduced to just operations that happen on bits, right? So you have an input into your program, there's a bunch of bits. Then you have the execution of a program, at which point the bits get shuffled around. And then you have the output of the program that is also represented by a bunch of bits. At any point, we can actually attach a debugger, right? And inspect the state of the program and inspect the state of a CPU registry and maybe even inspect the hardware itself and the voltage there. Everything is fully transparent, right? Now, in a quantum computer, it's different. Like the input phase is sort of similar, because if I want to input something into a quantum computer, then I'm really inputting my own classical information, right? And our classical information is 0-1 based. So I would just map this to states ket0 and ket1 and let quantum computer start its work. And then the output is also sort of similar to the classical output because, as we said, I mean, we can only observe the qubits to be in a state ket0 and ket1, in which case we can then map this to classical bits, and basically then that phase is the same. But it's the execution that's fundamentally different, because at this moment, the qubits inside of a quantum computer, they can explore this superposition state, and they can also take advantage of other quantum effects, which we don't need to talk about today. But the point here is that if I have three qubits that I started the calculation with, right, then for 3 qubits, I can have 8 possible outcomes, right? It's 2 to the power 3. So effectively here, during the execution of this program, I can have a superposition of all these 8 possible outcomes simultaneously. And this is what we call quantum parallelism. So quantum computers can take algorithmic advantage of superposition. And this is where some of their possible computational advantages can come from. And the way you can think about this, I mean, this is not a perfect way to maybe describe this, because that effect is super subtle. But it's a good way to at least begin thinking about this, is if you consider a function f of x, right? Now, on a classical computer, if you work with a function f of x, you basically have to pass different values of x separately, right? Like f of 0 and then pass 1 and then maybe pass 2 and 3 and so on. Now, on a quantum computer, you can actually create a superposition of all the possible values of x and pass that into a function and try to calculate from there. And so this is almost the opposite. And here's why. So if you consider, so this is the input into a quantum computer. And in this case, we have, I believe, 5 qubits. And then the input goes through a set of H gates. So these gates create a superposition in the quantum computer. And what now happens is that each qubit enters the superposition state. So if I have 5 qubits, I have 2 to the power 5, which is 32 possible outcomes, right? Like basically the calculation of this program would yield a number between maybe a 0 and 31. And so now I have the superposition of all these possible values existing out there in the vector space of this quantum program. And then the trick for writing a quantum algorithm is to steer the evolution of this program in such a way that the correct result, the one that the algorithm is supposed to reach, will get amplified, and the others will get sort of canceled out or pruned. And that's the reason why I mentioned that this is sort of opposite to what classical computers do, because you are not searching for the solution, but you're eliminating the incorrect solutions, if you will. And that is basically the way you should think about quantum computations. So now this leads us to RSA. And so RSA is one of the most widely used public-private crypto systems in the world. And the security of RSA relies on the factoring problem of large numbers. And RSA is maybe not as widely used today as it was in the past. For example, in TLS 1.3, you cannot even use RSA for key exchange anymore. But it's a good example because the mathematics are actually not very complicated. So I like to use it as an example of how quantum computers can actually attack classic cryptography. So this is how RSA works at its heart, right? Like you start by picking 2 huge prime numbers, P and Q. And you also pick an exponent E, although that is almost always 65,537. So it's almost always a constant. And then what you do is you multiply P by Q, and you get an N, and you publish that N, and you also publish your E. And basically, the N now becomes the public key, and the P and Q stay private, and they make up the private key. And so if somebody would like to encrypt something using your public key, what they do is they follow this formula. They take the message that they are trying to encrypt, they convert it into binary, which basically gives it a numerical format. They raise it to the power E, and then they calculate modulus with N. And effectively, what this means is that N is like the only variable here, and that is the public key. And so that produces a ciphertext. And now you can always recover the message out of the ciphertext, provided you have access to P and Q, so you use a different formula, but the P and Qs are there. So if we now sort of reduce this to the bare minimum, the security of the whole thing boils down to the fact that if you know N, you will not be able to find the P and the Q. And so here is a JSON Web Keys document that is published by Google as part of the OIDC protocol, right? So if your application is consuming tokens issued by Google, you can go to this URL, fetch the public information about the keys that are used to sign this token, and then you can validate this token. And you can see here there is an N. Actually, there are 2 keys, but there's an N, and this is the E, and it's the same here. This is actually 65,537, and this is the N. So effectively, if I now have the technology that allows me to take this N and find out the values of P and Q, as we said here, then I'll be able to self-sign any Google token, right? Like I will be able to impersonate any Google user. And of course, that would be a sort of a devastating attack on Google, if you think about this. But of course, if I have the technology that allows me to do that, then I have much better things to attack than Google, right? I'd probably go to my bank first. Or maybe not to my bank, maybe to your bank. But you get the point, right? Yeah, so let's now travel to year 1994. And this is cool because in year 1994, there were no quantum computers. They were purely theoretical devices. And then there was a computational model that was developed over the 1980s, predominantly by David Deutsch at Cambridge, where, so no quantum computers, purely theoretical devices. There was a computational model, also purely theoretical. And then Peter Shor from IBM at that time, now with MIT, he developed this theoretical algorithm for this theoretical computational model for these theoretical devices, where he said, okay, if all these things fall into place, then we can achieve pretty much exponential speed up when it comes to integer factorization, right? And so lo and behold, years later, quantum computers became reality. We can actually now try to run this algorithm there, and it actually works. And we can only run it for very small numbers at the moment, but it is correct. So how would you go about attacking RSA? Well, you'd follow a following recipe. You start by picking a number a that is smaller than n, that is relatively prime to n. And then you consider a function that looks like this, a to the power x modulus n, for different x's being integers. And you plot this function then, right? And you sort of observe how it looks like. And at some point, you will recognize, hopefully, that at certain intervals, it starts to repeat itself. And basically, that repetition interval is the period of the function. This is R. And once you have R, you can go to this very simple formula, and you can actually calculate the candidates for P and Q. So this is greatest common divisor algorithm. This is something that we have known since the time of ancient Greece. This is also very easy. So 1 and 3 are possible to be done easily on a classical computer. It's the number 2 that is prohibitively expensive. In fact, it's so expensive that we think that on the largest supercomputers, given the sizes of integers used in RSA, it will take millions, maybe hundreds of millions of computational years on the biggest supercomputers. So let's look at an example as factor 15, right? So let's now assume that Google switched to 4-bit RSA by accident and published n equal 15, right? So how do we attack it? Well, we set a to be 13 because it's smaller than n and it's relatively prime. Doesn't have to be that, but that's what we set. And then we basically plot the function, right? So if this is 13, so this is 13 to the power x modulus n. So that function is already plotted here. And you can see clearly that it actually repeats itself at intervals of 4. And then what we do is we take the R and we substitute it into this formula, right? So this is now a squared. A is 13, so this is 13 squared, 169 plus 1, and here is 169 minus 1. And so basically we have to find the greatest common divisor between 170 and 15 and 168 and 15, and those are 5 and 3. And these are really the factors of 15. Right, so this is a super simple example. Now, I mean, before we get any further, if you have any 4-bit RSA security, you should really run home and update because it has just been compromised. But you get the idea, right? So if we now scale this up, then this second step becomes really prohibitively expensive, and so we'll never actually be able to do this for the larger numbers. Now, what Shaw realized is that basically this problem here is roughly a problem from signal processing, right? And in signal processing, there exists a technique called fast Fourier transform, which can be actually used here for order finding. And on a quantum computer, we have a quantum variant of it called quantum Fourier transform. And this is basically at the heart of Shor's algorithm. I mean, Shor's algorithm is actually a hybrid algorithm. So basically, the step 1 and step 3 runs on a classical computer, and then step 2 runs on the quantum computer. And so thanks to the quantum Fourier transform, actually, there's this almost exponential speed up. But now you might say, but this is RSA, this is shit anyway, nobody wants to use it, maybe for some tokens. In TLS, we don't use anymore RSA. And that is a valid objection, actually. In TLS 1.3, it is forbidden. And we use elliptic curve cryptography actually a lot more. But as it turns out, actually, and this was already it's not like somebody realized it later. I mean, it was in the original Shor's paper. He basically showed that you can actually use the same algorithm to actually compute discrete logarithms over elliptic curves, over prime fields, which is basically the same problem. Fundamentally, it's about this order finding, and you can equally easy attack elliptic curve cryptography with this algorithm. In fact, you can actually attack elliptic curve cryptography even easier. Just the mathematics is more complicated, but fundamentally, in terms of resources, so this is a paper from Microsoft from, I think, maybe 7 years back, where they basically show that the amount of resources is actually lower in a quantum computer if you'd like to attack elliptic curve cryptography than you'd like to attack RSA. Now, the reason why we want to use elliptic curve cryptography everywhere right now over RSA is different, because with RSA we have this sort of long-lived session keys, right? So if you compromise the private key, then you can decrypt a huge amount of information, right? With elliptic curve cryptography, you can sort of derive these things much more often. So that is fundamentally the reason why we want to use elliptic curve cryptography. Now the question is, of course, how realistic this is, or what are the timelines for this attack? Now, basically where we are at the moment with quantum computers is that they are small and they make a lot of errors, right? We think that maybe this year, maybe next year, we will reach a point where there will be a quantum computer that actually can no longer be efficiently simulated on classical hardware, even taking the largest supercomputers in the world. And of course, this boils down to the amount of qubits that you'd like to simulate, right? Because every time you add an additional qubit, the vector space of the program doubles, right? So if you have 3 qubits, you have 8 possible outcomes. If you have 4 qubits, you have 16 possible outcomes, and so on. Every time you add the next one, it actually doubles, right? So it grows exponentially. And so by the time you reach about 32 qubits that you like to simulate, you run out of memory on like the consumer devices. And by the time you reach into 50s of qubits, then you run out of memory on the largest supercomputing clusters in the world. Now, by the time you reach 260 qubits, actually the number is so large that it's actually larger than the amount of atoms in the entire observable universe, which basically means that at that point we would have to convert the whole universe into memory to be able to simulate such a quantum computer. Now, we have good reasons to believe that we will scale them up into thousands, maybe millions of qubits, but we will see. So in any case, the Global Risk Institute does this annual survey of like top quantum computing scientists that are involved in the field, just to gauge their feelings about where the field is. And one of the questions there is very relevant for us today. So when do people think that RSA will be broken? And just about everybody agree that this will happen in 30 years, right? About half of the people think that this will happen in about 15 years. And then some optimists think that it will happen by the end of this decade. So now I'll let you draw your own conclusions from this. Probably the first thing that jumps to mind when you look at this is probably like, I don't care, right? Like it's so far away. The counter argument to this would be that it's already too late. Because of course, if you are a super evil threat actor, like a state actor, you harvest now and you come back to this data later, right? When you have the capacity to decrypt it. Now, then you have to define your threat model, and is it really important that some data comes out with a 20-year delay, right? But maybe some data should never become public, right? In fact, if it's promised to be encrypted and safe, then maybe it should never become public. So that is really this question, right? Like, at which point do we switch to post-quantum cryptography? And probably we should switch as soon as possible. So asymmetric cryptography is basically doomed because there is really no alternative, or there was no alternative until recently. What about symmetric cryptography? And for that, we have another paper from 1996 by Love Grover. And in this paper, he showed that you can have a quantum search algorithm through an unsorted data set. So basically finding a needle in a haystack with a brute force with a quadratic speedup. Now, a quadratic speedup is actually something that is super impressive, if you think about this. Because it means that if you need 100 steps on a classical computer, you only need 10 steps on a quantum computer to do this. But the thing is that it's impressive when you go from 100 to 10. But if you have a huge number of steps, and then you achieve a quadratic speedup, so you take a square root of that huge number, it's still a huge number. So this is a technique that we can use to brute force AES, for example. But the thing is that it doesn't really help much, right? Because classically, to brute force AES 256, you need 2 to the power 256 steps. Now with a quadratic speedup, you only need 2 to the power 128 steps. And so that is great, but it's also still very difficult. And so you can completely counter the computational advantage of quantum computers here by simply doubling your key size. And so here's the summary of everything we talked about so far, right? This is not an exhaustive list of algorithms. It's just sort of to highlight the general direction that we should be thinking about stuff. If you have symmetric algorithms, then they should be considered to be half as powerful against quantum computers, right? So basically, AES-128 should no longer be used. And then if you have asymmetric encryption, then you should consider all of that to be vulnerable. And so this leads us to post-quantum cryptography. So in 2016, the National Institute of Standards and Technology, and national here means in the US, they announced this post-quantum crypto competition, right? And the goal was to develop a new algorithms that would actually be resistant to quantum attacks. And in 2022, they announced the 4 winners. And so they have some of the best names that you'll ever encounter in technology, like Kyber and Dilithium, right? I mean, these are clear Star Wars and Star Trek references. Only one of them, Kyber, I mean, you can see that it has a different emoji. I paid a lot of attention to creating these slides. So this is the only one that can actually be used for key exchange. So this is the only one that we can actually put into TLS. The others are just signature algorithms, so we can use them for signatures. And 3 of them, Kyber, Dilithium, and Falcon, are actually based on the branch of mathematics called lattice algebra. And we had a slide where I tried to explain the RSA security a little bit. So I wanted to include a slide about lattice algebra as well, this so-called learning with errors problem. This is vastly simplified because the mathematics is much more complicated. But effectively, it boils down to this. You start by picking 2 vectors in this lattice space. And calculating a dot product between them is something super easy. And so basically, this gives you a number. And then you introduce an intentional error, right? So this is something that you have to choose from a specific distribution, but it's sort of intentionally now skewing the result. And then you pick the modulus for the arithmetic, which basically sort of confines it to the specific range, because with modulus, it sort of wraps around itself mathematically. And then you get a t, and this is effectively a number. And so what you do is you publish the t, the q, and the a, but the s vector you keep private. And this is the private key, effectively. And the strength of the whole thing boils down to this, that if you know t and a and q, you will not be able to recover the original s, and primarily because of this intentional error that was introduced. And so this is really at the heart of Kyber and Dilithium, for example. Now, last year in August 2024, so just, 4 or 5 months ago, these 3 of these these competition winners, were actually standardized as official standards. And so Kyber became, actually, so they all lost their cool names, sadly. So Kyber became MLChem, Module Lattice-Based Key Encapsulation Mechanism Standard FIPS 203. And then Dilithium became MLDSA, Module Lattice-Based Digital Signature Standard FIPS 204. And the same with Sphinx, it became FIPS 205. So I personally continue to call them Kyber and Dilithium because it's so much cooler. But basically, what does it mean that they were standardized? I mean, it just means that now everybody's encouraged to actually go ahead and implement that in the software. And that is now happening, and there is a lot of standardization effort across the industry ongoing around these topics. So the major thing, of course, is TLS, right? So there is a draft for this. This is not published yet as final standard, but it's been ongoing, actually, even before this MLChem standardization, just for Kyber. So the latest one was published, notice the date here, I don't know why, but somebody did this on the 25th of December. So this is the latest state of it. And this basically describes how post-quantum cryptography should be integrated into TLS 1.3. And this is actually a hybrid algorithm. So it actually does both elliptic curve Diffie-Hellman and Kyber, MLChem, at the same time. Like, it actually does both of them and then takes the secret and then does the key derivation over both of them and produces one final one. And the reason why it's done like this is because there is still a bit of a worry that we are trying to make things better and we will make them worse by switching purely to Kyber. Because with elliptic curve cryptography and RSA, there's like 50 years almost of experience when it comes to trying to attack it and also implementing it. Because actually the problems can come from both sides. So somebody might suddenly come up with a wonderful new technique to actually attack Kyber, maybe even on classical computer. This is actually highly unlikely at this stage because that algorithm has been out there for now almost a decade. But the second problem is actually probably bigger, that the implementation might contain errors, right? And especially as the lower level stuff, like if you consider like OpenSSL, for example, the algorithm implementation there would be in C, right? And this is not a language that really is very forgiving with mistakes. And so the mathematics might be sound, but there might be an implementation issue at some level. But in any case, this is now supported by all the major browsers. There is one notable browser that is missing here. There is, of course, the Internet Explorer of today, Safari, right? But all the other browsers, they support, by default, this post-quantum hybrid Diffie-Hellman Kyber TLS 1.3 key agreement protocol. There's actually a nice website, this one. It's pqcloudflareresearch.com. You can basically go there and open it, and it will tell you whether you are using a browser that supports post-quantum cryptography. And notice that if I open this in Safari, right? So it says this is not post-quantum secure, and here it is post-quantum secure. Now, this used to be a flag, but now it's enabled by default, in fact, in all these browsers. Now, is there any overhead here with Kyber? There is quite some, actually. So this is just a comparison between various algorithms. And MLChem, so Kyber comes in like 3 strength levels, and 768 is the one that is used by default. And you can see here that the public key and the ciphertext, so basically this is what comes down from the server, and then the ciphertext goes back to the server from the client. So you have 2 kilobytes of overhead of data that needs to travel during the TLS handshake, which is much less, which is much more than what happens in Diffie-Hellman, for example. Because they're actually, I mean, it's different because the ciphertext doesn't travel back, and so it's difficult to compare, but it's less data, like a lot less, actually. And so there could be like IoT devices, for example, some older devices that might have trouble switching to this because the amount of data that travels during the handshake is just so much larger. But on the flip side, the algorithm itself for Kyber is much quicker to execute than the calculations that are needed in Diffie-Hellman, on elliptic curve cryptography with Diffie-Hellman, and in RSA especially. So actually, computationally, you can actually do more operations per second with Kyber than with these other algorithms. Now, Cloudflare has been actually leading the adoption when it comes to post-quantum security. They already support this hybrid Kyber Diffie-Hellman key exchange already going back to 2022. And they actually publish a report how much of traffic to their servers is post-quantum protected because they have it enabled on all of their endpoints by default. And basically, this is data from 2024. In the beginning of the year, there was only about 1% of traffic that was post-quantum protected. And now it has grown to almost 1/3. Now, TLS is, of course, just one thing. But, of course, we have the messaging apps that are also in need of being post-quantum protected. And Signal, there was the first one. They adopted Kyber into their own, they have their own custom protocol. And they adopted Kyber in there, and they now call it post-quantum extended Diffie-Hellman. And they did it already back in 2023. So Signal is a good choice if you are using messaging apps. But surprisingly, there's an even better alternative now, because Apple has updated their iMessage app, or the Messages app, as it's called, to use post-quantum cryptography as well. They call the protocol PQ3. And they actually did this, basically, it's roughly the same as what Signal did, except they also introduced ongoing rekeying. I think it's every 50 messages that they actually generate a new key, which means, of course, that if somebody wants to capture your traffic and then decrypt the messages, they have a lot more things to decrypt rather than just one key. So these are the two messaging apps that support post-quantum cryptography today. The others don't. So these are the ones that probably are better to use, if you ask me. And now if you're a developer, of course, you should go and implement stuff, right? Now if you are a .NET developer, then you are out of luck because there is no official support for post-quantum cryptography in .NET. There is an open issue that is currently slotted for .NET 10 for adding official support, but I'm not sure whether anything there will happen because there is no movement there at the moment. So we will see. But in any case, that still has a longer time frame. But if you are a .NET developer, you can still use this Bouncy Castle library, which is actually a library that exists for Java originally, but it has a .NET port. And so it's always released sort of in two versions in parallel. It has this is the official logo, but it's one of the coolest logos in software, right? So that alone is worth giving it a try. So we are going to look at some Bouncy Castle code in a second. Just this is the final slide I wanted to include. There's this open quantum safe project, which is basically like the center of the universe, if you will, for post-quantum cryptography. This is a project that's coordinated by University of Waterloo in Canada. And out of the many things that they do, they have this Leap OQS, which is a C library that provides implementation of all the quantum-resistant crypto algorithms in C. And because it is in C, you can then use it really everywhere. And since this month, they started to produce bindings for the higher level languages. So I saw that there is now libOQS with bindings for Python, for Java, for Go, and I would expect that others will come also soon. They also have an OpenSSL provider for OpenSSL 3, so we can actually use that together with OpenSSL. And from what I saw, the official implementation in OpenSSL that is coming now for MLChem will actually be based on libOQS. So this is really like the thing that is going to basically, underpin security of the whole internet going forward. All right, so let's now look at some code. So we are going to start with this. Is this large enough? Yeah, good. It's too large for me, but I have to. So we'll start with just a simple console application. And here we'll just look at some Bouncy Castle APIs just to be able to follow the flow, right? So in this case, we will do MLChem. And we start with step 1. And so basically, we are going to do the same thing that will happen in TLS 1.3 if it was purely based on MLChem, right? So we start with this step 1, which effectively means we are telling Bouncy Castle we are going to use MLChem 768, and we would like to get a pair of keys, right? So this is the pair of keys for Alice. So we now have a public key and a private key. And they will be displayed here when we run this. And of course, private key has to stay with Alice, and then the public key is something that she can share with Bob. Now in the second step, Bob will now use the public key of Alice, so this is this one, and what he will do is he will initialize the process called an encapsulation, which effectively means that he will generate a new shared secret, a 32-byte secret, and create a ciphertext based on Alice's public key. And that's basically what happens here. So there is a ciphertext and a secret. I mean, these are empty arrays first, right? But then they are actually filled with this operation. So at this point, Bob has a secret, and so he keeps this secret. But the ciphertext he now sends back to Alice. And so this is, again, in the client-server scenario, this is now the client sending back the ciphertext to the server. And now in step 3, what Alice does is like the reverse, right? So she will decapsulate now the secret out of the ciphertext. And in order to do that, she has to have the private key. And so she has the private key, and then basically she can run the decapsulation. And so now she has a secret, and that secret should be identical to the secret that Bob has. And at that point, they can actually switch to symmetric encryption and start sending each other messages that are encrypted with AES 256. So if we run this, we should see that it works. I mean, it has a green checkbox, so that proves everything, right? So these are the keys. I mean, the keys are really long, right? That's why they are truncated. Now Bob's secret is this. And then the ciphertext is also long, because remember, the public key that travels from the server to the client will be over 1 kilobyte, and also the ciphertext will be over 1 kilobyte. But then what Alice recovers out of the ciphertext with the decapsulation is the same secret that Bob has. Right? So it sort of worked. So now let's look at the same process, but now for MLDSA. So this is a signature algorithm, so it has a different first step, because first we need some text that we are trying to sign. So now Alice is preparing some text that she will sign. She then does something that is very similar to what we did before, which is generate a key pair. But this is not the same key pair as we used for key exchange, right? Because we need a different algorithm, so this is MLDSA key pair. And now she has a public and a private key. And of course, just like before, the private key stays with her, but the public key is something that she can share with Bob and with everybody. And then in the next step, Alice will sign the data, right? So to sign the data, she needs this MLDSA signer. And she initializes it using the private key. And she also passes the raw data. So this is actually plain text data that she's trying to sign. And then she obtains the signature, right? So this API is a bit awkward. I mean, it's stateful, but that's how it is implemented in Bouncy Castle. And what we will now do is we will print this out, and we can then send the plain text message to Bob and also the signature to Bob, right? So that he can verify this signature using the public key that he already got against this message. And so this is what Bob does. He also initializes the MLDSA signer, but now this time using the public key of Alice, because he doesn't have his own keys and it would then not work, right? So it has to be the corresponding key. And he then sort of passes the data into the signer and then runs the verification against the specific signature. So let's try this out. And basically, so this is the original pair of keys from Alice. This is the raw text. This is the byte array representing the plain text. This is the signature, and then the verification succeeded. So basically, these two things, these are the building blocks that you can now take and start using in implementing different workflows in your applications, right? The most obvious thing that comes to mind would be to take MLChem, so Kyber, and use it for some sort of an end-to-end chat encryption, right? So this is what I wanted to show you next. This is by no means a reference implementation, right? It is just a starting point that shows how you can start sort of integrating these algorithms. Because typically, if you like to put something out on the market, then you really should follow an official protocol like the Signal protocol, right? But that makes the demo a bit more difficult to follow. So what we'll do is we'll go here. And here I have a Blazor application. And the whole thing is basically 200 lines of code, and half of it is HTML. And in fact, the HTML is so bad that it actually proves that this was not written by AI. But this is a Blazor application. This is a Blazor chat application. And it's a Blazor WASM. And I think this is a cool thing about Bouncy Castle, because it has no native dependencies. So all the algorithms are actually implemented in managed code. So you can actually take Bouncy Castle, and you can actually compile it into WASM as well. And it then runs in the browser locally entirely. This is not possible with the crypto APIs of .NET, because they have native dependencies. So that is quite nice. So we have this Blazor WASM chat. I will actually start by showing you this app. So I'm going to run this app. So because it's a WASM app, it runs entirely in browser. We still need some medium for messages to travel between one user and the other. And for that, we have a Signal R server, so I'm going to start it. And now, this is the chat. And this is the other browser, right? So I've now launched this application. So I can enter this chat as Filip. And I need a second user. I need a second name. Bob. Bobby. Little Bobby. Little Bobby tables. So what now has happened, I have to explain this because the HTML is so bad that you probably have no idea. So basically, Filip now sees that there's one other user than himself, right? So he sees that Bobby is there, and then Bobby sees that Filip is there. And they both have now their public keys. And the reason why they have their public keys is in the code here, in this Blazor code, basically whenever the page gets initialized, we actually generate an ML-chem pair. So there's a private key and the public key. And the private key is kept in the browser locally, but the public key is sent to the server, right? And so it's then available with the list of users to be actually pulled from the server. So now Filip knows that this is Bobby with his public key, and then Bobby knows that this is Filip with his public key. And they can now establish a secure session. It doesn't matter who does it. It just matters that it is done, right? Because effectively, it's like the Alice and Bob scenario that we had before, right? It was Bob that was doing the encapsulation based on the public key, right? So now any of them can actually start the encapsulation process. So Filip will do this based on Bobby's key. And now what has happened is they have negotiated a shared secret. And this is now a 32-byte secret, so it can be used for AES 256, right? So I can now send hi. And now what happens is that this message is encrypted with this AES key. This happens entirely in the browser as well, and then travels through the Signal server in an encrypted format, and it's decrypted in this browser, right? So hi, and then it can say bye, right? So there's a lot of effort for this conversation. So just to have a look at the key aspects here, right? So there's this negotiate secret, which is basically the function that that was called when I pressed on this establish secure session. And you should recognize this is basically the same code that we were looking at moments ago, right? And what happens is that the user that initiated this would use the public key of the other user and then run the encapsulation. And then the shared secret stayed secret within the browser. This is local data. This is just a local field here. But the ciphertext was sent over SignalR to the other side. And then it was actually picked up here, right, on the other side, and then the decapsulation process ran using the original private key that is actually corresponding to the public key for which the encapsulation was done. And this way they have the shared secret. And then for the outgoing messages and the incoming messages, they simply use AES here, AES encrypt, AES decrypt to do this. Now again, this is not an example to show you sort of super robust end-to-end security, because there are some questions that we should be answering here about the role of the server here and so on. But it's a good way to at least begin thinking about how you can actually implement these algorithms into something useful. And so the final thing I want to show you is also how you could integrate MLDSA into quasi-real-life scenario. And for this, we have here an identity server, right? A Duende identity server. I mean, there is a Duende booth just right outside. So if you've done any like token issuing on the .NET platform, I mean, chances are that you have used this because that is probably the best option. And so what I've done as part of sort of my way of spending free time, I've set up some integration libraries that basically allow for taking the dilithium algorithm from Bouncy Castle, so MLDSA, and have it seamlessly integrate into various parts of .NET, like for example the Duende Identity Server or ASP.NET Core, because it is not supported out of the box. And so here I have this helper that basically, as I bootstrap my identity server, I will say I would like MLDSA support by additionally by MLDSA support. And this is actually coming from a library that I call StratWeb Dilithium. I mean, there's a family of these libraries. So this is from NuGet. And basically what it does, it just tells identity server how to deal with MLDSA in various places where it needs to deal with cryptography. And so one thing that I can do now is when I configure my identity server, I can say, you know what, if somebody would like to obtain a token for this particular API, they will have to go through MLDSA 65. So this is one of the, it's like the mid-security MLDSA variant. So let me start this IDP, .NET Run. And what I can now do is I can go and fetch the JSON Web Keys document. And notice that the JSON Web Keys document now reports only one key. And this is not an RSA or elliptic curve cryptography based key, but is actually a key that is using MLDSA 65. And the way this is reported here and integrated is also based on another standard, because there is another emerging standard that basically tells us how to integrate MLDSA into various signature algorithms and into JSON Web Tokens. And this is basically the public part that is needed to then validate such a token if a token was signed with this particular key. So far so good. So now we just need an API that will actually accept tokens that are signed with MLDSA. And for that, I have an ASP.NET Core API. And out of the box, it would not work, right? So I actually have a line here that makes it work. So let's comment this out. And let's start this API and see, because this way you will know that I'm not lying, which I do a lot. And so this is my test application. So it basically just fetches the token, and then we'll call the endpoint on the API, right? This demo endpoint. And the demo endpoint only responds with a hello world. So if I now run this application, this is the token that was obtained, and you can see that I got a 401. And the reason why I got a 401, if I go here, you will see that the signature validation failed because .NET out of the box, ASP.NET, doesn't know how to deal with this MLDSA signatures. But that is a good sign because it means that we have a token that is signed with MLDSA. So I can actually try to, oops, I was trying to copy this. I don't know if it worked. Because I wanted to show you this token, jot.io. Come on. No, it didn't work. That's my airline booking code, by the way. Where's my token? Here. One more time. Ooh, copy. Oopsie. And now, where is it? Decoded, there you see. So the algorithm is MLDSA 65. So the token contents are sort of normal stuff that you would expect, but it's actually using an algorithm that is post-quantum enabled. So let's now come back here. And basically this, and call this, right? So this comes from another NuGet library that allows you to integrate with the DTM strat with DTM ASP.NET Core. And it basically tells ASP.NET Core what to do when you encounter these types of tokens, right? And how to validate them. So let's now restart the API. And now it's running. And let's run the demo app as well. And now it has responded. And there should be a line somewhere here, successfully validated the token, right? So it is as simple as that. And so these are these sample ways of how you can actually get into post-quantum cryptography into your own apps in a way that actually doesn't require much work. So I think this is everything that I had. I need to check. There you go. I think we ran out of time anyway. If you'd like to see those slides, then they are online. They are a web page. And then if you'd like to see those demos, they are also online on GitHub. And yeah, I think that's everything. Now, because we ran out of time, I don't think we can do questions. But I timed it perfectly because I didn't want any questions because there are always smarter people than me. And then it's embarrassing. But if you'd like to talk about any of this stuff, then just grab me afterwards. I think this is a safer space to discuss things. Thank you again for coming, and I hope this was not an... Thank you.